Why is it rational? Well, we use objects to do physics, not concepts. And we don't move concepts around. And that separates us from the rest of the pack. So we're a little different than everybody else here. Anyways, today we're going to be talking about the Slit Experiment and these two individuals here, Matt O'Dowd and Sabine Hossenfelder, and we will have them tell us what they believe or what they think about the Slit Experiment. You won't hear it from me, you'll hear it from the horse's mouth. They have not figured out in the last 200 years what causes the Slit Experiment, how it works, what the mechanism is, and that's what you'll hear from them today. But before we do, I need to talk a little bit about something that happened this past week. A couple guys, Aetherists, right? They came over and they insulted me. Can you believe that? They insulted me. They offended me. Is it something they said about my mother or something? No, that would have been okay. The problem is that these people say that they have the same theory as I do, but they don't understand why. I have a problem with the ether. So, what can I say? That was very offensive. And so I'm going to talk a little bit about, as an introduction today, about the Aetherists, the electric universes, the plasmoids and thunderbolters, and flat earthers. In other words, what they believe. Why are they irrational individuals? Okay, what is irrational about their theories? Okay, and that's where we're at today. These people really believe that they have theories, valid theories that they like to propose out there, and I do admire their enthusiasm, but no, their theories are all irrational. So why are they irrational? Well, let's go over that. So we learn a little bit about the scientific method and how and why these people are so far away from it. Okay, so here's the scientific method that they avoid, and that's, again, Aetherists, plasmoids, and the flat earthers. The plasmoids are from the electric universe, and they don't follow the scientific method. That's where it all starts. They're screwed up with that. And you say, well, what do you mean? Where are they failing? Well, we get taught a certain scientific method in school, and it looks more or less like this, okay? I call it the mathematical method because it has absolutely nothing to do with science, okay? And essentially it's a method of research of how to go about discovering things in your dark basement, and that's fine, but that's not science. When you come to conference, we want you to explain something. That's not what they do. What they do is they say, oh, look, this is what we did. We're scientists because we observed, explain tentatively, which they never do anyways. They call it a hypothesis. Becomes a theory when it's proven, I guess, or when the majority vote for it, raise their hands and vote. They talk about prediction. They do predictions. Experiments. They describe mathematically, come up with equations, right? They measured, right? And they invent technology to confirm the theory that says, we have GPS, we have computers, that proves, relativity and quantum mechanics in their minds, right? Then they convince the other colleagues, the mathematicians. So they talk about proof, truth, what is a fact, right? They verify against through measurement. One guy verifies the other guy. If they do this verification, they call it falsification, right? Then the theory passes that mark, and then they win prizes and do the talk circuit. We say none of this has anything to do with science. None of it. Especially two pillars, you could say, that they always talk about as far as science is concerned, which is experiments and math. In science, we do not use math at all, and we do not do experiments at all. People say, Bill, did you misspeak? Did you say that correctly? Yeah, let me say it again just in case. In science, we do not use math at all. We do not use numbers. We do not use measurements. And above all, we do not do experiments. In science, we explain experiments, okay? So that's where all these people fail, because they have followed this so-called scientific method, or this notion of science, since the 17th century. People like, William Gilbert, Torricelli, Galileo, Robert Boyle, his right-hand man, Robert Hooke, all the way to Newton and beyond. All these people have always thought that science is about running experiments and doing equations. And here, let's run an experiment to find out if what they say is true. Let me get this out of there. Give me a second here. Here, I'm going to run an experiment, okay? You tell me. Okay, here's an experiment. I've got a spoon, right? I'm going to let it go. I did the experiment. I did the observation. I observed it. You observed it with me, I guess, right? Let me do it again. Just it's got to be repeatable for it to be scientific. So now we have a repeatable experiment, okay? So am I a scientist because I did an experiment? I mean, should I get a Nobel Prize because I let the spoon fall? And I could even measure and say, hey, it's 9.8 meters per second square. That's the acceleration of gravity. Yeah, so what? Science is about something more than that. Hopefully, science is about explaining the cause. What caused it to fall? That's where you have to use your brain. That's where you got to try to figure out Mother Nature's secret. It's like watching a magician, seeing a magician on stage, and he cuts the lady in half or makes the rabbit appear out of the hat, right? And you say, oh, how did he do that trick? Well, just observing and doing the magic trick, that's not science. Science is figuring out how he did the trick. That's where you have to break your brains. And that's where we're at today. We don't have any mathematicians that have figured out how this universe works. They don't know how gravity works. They don't know what light is. They don't know how an atom works. They don't know anything. They cannot explain a single one in a rational manner. That's where the problem is. And so, what is the scientific method? The one that we're going to apply here against these the plasmoids and the Aetherists and flat earthers. Well, this is the scientific method. Okay, so let's look at it very carefully here. We have a hypothesis. Known as the set of assumptions. It's known as a hypothesis, and so a hypothesis is not a theory. It's not an explanation. That's not what a hypothesis is. Hypothesis is just the assumptions that you have to make in order to explain later on the theory based on those assumptions. First, you need to present the object. We're talking about physics here, by the way, not philosophy. You need to present the objects. You can't do physics without objects. So you need to present the objects that are going to serve as actors in your theory. That's the first thing that you need to present. Without anything in front of you, if there are no objects, there's nothing happening. The next one is you need to have definitions for the key words, for the strategic words that are going to make or break your theory. So if you talk about, gravity, what is gravity? You have to give some explanations or some definitions for these words, the ones that you're going to use to make your case. And they have to be rigorous definitions. You have to be able to defend those definitions also. And then we move on to the initial scene. You have to start out at the initial scene. And then set it in motion. In other words, you got to start at frame one of your movie and then, move on to the rest of the film. And we call it the statement of the facts. It's not the facts, it's the statement of the facts. Why? Because, you have a prosecutor and you have the defense attorney, and they're going to try to convince the jury, to sentence the guy to death because he killed someone, right, for example. And so the prosecutor is going to say, look, he's the guy who murdered the victim, who stabbed him 20 times. And the defense attorney is going to say, well, no, there was serial killer in the region, and he's the guy who did it. So they have different notion of the facts of what happened there. And so you have to start there. You have to start at what your statement of the facts are. And again, that's why we say it's the initial scene, the statement of the facts. We have the theory, the explanation, meaning we were looking for the causes, the mechanisms that underlie physical phenomena. And then the conclusions, which includes the interpretations and corollaries. Okay, so that's essentially what we're saying is the scientific method. The scientific method is a method of delivery of your theory. You have to go in some kind of order for people to understand your theory. And that's what we do at the conferences. You go to the conference to explain something. You don't do what Faraday did, which he went to the conference or a group of people and he said, let me do an experiment for you. And so he did an experiment and said, look, this magnet attracts at that one. And I discovered something new, that this magnet attracts this one, and or the electricity flows in such and such way. Yeah, those are observations. He hasn't explained anything. He hasn't shown that he used his brain at all. Oh, he says, I discovered this by sheer coincidence, maybe. Okay, so that's the first problem. They don't follow the scientific method. What's the second one? They avoid pointing to the objects they invoke to explain their theories. They never point to their objects, and especially the Aetherists. We ask them to point to the ether. I want to see what it looks like. What are you talking about? And they never do. They say, oh, Bill, you're doing semantics. You're doing word salad. For them, it's just words, noise going through their ears. No, you have to point to the objects that you're going to use in your theory, that are going to act in your theory. Otherwise, what am I staring at on the screen? You're showing me a movie, and you don't mention what those objects are. You use words such as energy, maybe field, and we don't have any idea what those are. Certainly, they're not physical objects. So what are you talking about? And this is what happens with ether. They say, well, I can't point to the ether. I've never seen the ether. Ether just covers all of space, etc., etc. And they never point to the ether. We don't know what they're talking about. It's a medium. It's a fluid medium. Whatever that means. Medium, anything is a medium for that matter. You don't have to point to it. But in physics, we do. And so we start with the definition of what an object is. What is an object? And this is where the problem starts. No one has defined the word object in the last 10,000 years, especially the mathematicians, because they don't deal with objects. So they never found a need to define the word object. That's where the problem is. And so I say the definition of the word object destroys all religion. Once you define the word object, ether goes away, plasma goes away, electricity goes away, all these words go away. You can't use a single one of these words. Can't use force, field, wave, all those get washed out because of that definition. That's why it's an important definition. And the golden principle of physics is that you can't do physics without objects. Physics requires an object. Imagine if we raised all objects from the universe, what's happening? What are you staring at? There's nothing there, right? No, you have to have somethings in there, right? Otherwise, you can't do physics. And an object is not that which you can see or touch, which is what people have, this notion. And here I'll give you an example. Again, the same example as before. Let me move this a little out of the way. Give me a second here. Okay, so here we have a fork, right? And we let go of it, right? And people say, well, there's nothing that I can see or touch at the bottom, nothing I can see or touch on the top except air, right? And so nothing is in contact with the fork. And so they start using words invented by the mathematicians. They say, oh, it's the mass. Oh, the energy, the force. They start using all these words. None of them are physical objects. So I will not understand the cause of what's forcing this to come down by using those words. I can't use the words such as field and energy and force and so on, because none of them are physical objects. I can't say that the force caused this to fall down. That's an irrational statement. Force is a concept. Force cannot cause anything to happen. No, the fact that I can't see or touch does not mean that there is not an object here. And that's what killed everybody in the last 10,000 years. People thought that an object intuitively was that which you can see or touch. Since we can't see or touch anything here, there's nothing there. That was the conclusion. And that's an irrational conclusion. Okay, and that's because of the definition of the word object. No, an object is not that which we can see or touch. An object is that which has shape. Not all objects can be seen. Not all objects can be touched. That's the conclusion. Okay, and so an object is that which has shape, right? Shape is the universal property of all objects. There is not a single object you can imagine that you can name that does not have shape. There's no object you can imagine, right? And concepts don't have shape. And so what's the issue? The issue is that, we can't see the air, for example. That's an example, right? And are we going to say that air is not a physical object? It's made out of atoms, just like your chair, just like your table. So why is the table an object which is made out of atoms, right, and not the air, which is also made out of atoms? One you can see and the other one you can't. Why can't you see the air? I mean, you had problems with your eyes, maybe, some astigmatism, maybe. And we certainly cannot see or touch the table that's on the other side of the universe, in where the Klingon lives. So does that mean that the chair and the table he's sitting on right now and the table he's eating on, none of those are physical objects because I can't see or touch them? So we have a problem. Do I have to run a test? Like the table and the chair that's on the other side of our planet in China, those are not objects. I have to go over there, touch them, see them, and then they become objects. The word table is not an object always. The word chair is not an object always. Whether I touch it or not, whether I run the experiment or not to see and touch them. So yeah, those are irrational definitions, but those are the definitions that people casually, intuitively just go with. And those are wrong definitions for physics. We cannot use those irrational definitions in physics. In physics, that which has shape. That's what an object is. So what is the shape of ether? And that's when they say, oh, Bill, you're doing semantics. Yeah, it's semantics because it destroys their religion. That's why. That's why the word object, the definition of the word object, destroys all religions. Space-time, not an object. Space-time is a concept. We can't say that, gravity is the bending of space-time. No, that's an irrational statement. So, and so on and so forth. Okay, so then what's the other problem? The problem is that they fail to define the key words they invoke to explain their theories. They think it's all word salad, just noise going in their ears. And so we need to find out what a definition is. What is a definition? A scientific definition. No one has defined the word definition. So we don't have a definition of the word definition, and because of that, we don't have any valid definitions out there because nobody checks them for rationality to see if specifically that they can be used consistently. So let's find out what a definition is. Here we have it. Here we go. Definition, the scientific one, right? Limitation placed on the extent or usage of a word. Okay, I always give the wrong example, but it's a good example. I like it on the one hand, but it's the wrong example. I just want you to know that because I'm going to mention objects, not the words that I should be using. But it's a good way of presenting the problem. I say it's got wings and it's white. What am I talking about? Well, it could be a bird. It could be maybe a swan, and it could be the White House. You're right. But if I say it's a bird, now I exclude the White House. And if you keep doing that, you eliminate more and more things. Finally, you say, okay, I know now what a swan is because it's got all these properties that no other thing has in the dictionary. And so that's one way of zeroing in. In other words, what you have to do is you have to put a limitation on the word, the extent and usage of the word. Definition is not the same as meaning. Okay, people say that's the meaning. No. Meaning and definition are two different words, two different notions. Definition is what a prosecutor proposes, right, to the jury. Meaning is what the juror gets out of it. Okay, the meaning is on the receiving end. It's on the emitting end. That's what definition is. Okay, And if a definition is on the emitting end, meaning is on the receiving end, prosecutor issues definitions, the juror infers meaning. Okay, so that's the way it works. And people say, well, Bill, I don't like your definitions. It destroys my religion. And so, I don't like them. I like my definitions better. No problem. The way we do it in science is not by liking. And we don't use authority or, tradition or anything like that. Here's a rundown of those. Okay, here we have the fallacy of tradition, right? Oh, we've always done it this way, for hundreds of years, and you're going to change that now? Yeah, we don't care how we done it in the past, okay? That's not a reason to not give a proper definition. If we did it wrong for 10,000 years, then we got to change it. Just as simple as that. And then we have the fallacy of authority. This is what the dictionary says. This is what my teacher told me. No, that doesn't work in science. And then, all the fellows over there at the math club, they voted for my definition. We don't care about that either. It's not a voting issue. It's a question that you must defend your definition with sword and shield, right, against all attacks. Okay, so that's the way it works. And so all my definitions are very crisp, very unchallengeable, but, it doesn't mean that someone doesn't have a better mousetrap than me. It could happen, yeah. But the way we do it, again, we don't invoke authority, we don't invoke tradition, democracy, any of those. What we do is we fight for our definition. We defend them. And you had better have a good definition. If you're going to defend it, you better work on it quite a bit. A lot of these people come over and they don't work on their definitions. They say, well, that's not important. That's semantics, word salad. Science is 150% word salad, using your terminology. Okay, so you better have good definitions, because that's what's going to make or break your case. The definitions of the words you use. And ether is a prime example. Ether is an irrational term because people use it as a physical object, as a medium, as they call it. Fluid medium, fluid. No. Ether is not a medium. It's not an object. It's not a thing. Okay, and it takes, an ether is 10 years. Sometimes they never even achieve it after 10 years. It takes them 10 years at least to figure out why ether is not a physical object. And that was the problem in the whole 19th century when they used the ether from beginning to end of that century. They never defined the ether. They always assumed it was a physical object. They thought about it as the Greeks did, meaning a bunch of particles that form this background, right? And they said, well, these particles vibrate up and down, and that's the wave, the electromagnetic wave. That's more or less the sense that they had. So they had it as a medium, like water, like air. That's the notion these people had. And no, it's not a medium. Air becomes a medium only if it has shape. And air is a medium. It does have shape. So does water, by the way. And people don't always understand. They say, what are you saying, Bill? Water doesn't have shape. And neither does air. Yeah, air and water hopefully have shape. They're made out of atoms, so they better have shape. And the way we prove it, to all these people, the way we convince them, twist their arms, is we send the astronaut out into space with a little balloon. You can put air or water in there. We don't care either way. You pop the balloon, and suddenly, all this water, this air comes out. We'll color code the air so that you can see it, right? We take a snapshot of it. In the snapshot, nothing moves. We have a still image of air or water. Is there a shape there? It's a yes or no type of question. Don't tell me, well, what is the shape of air? What is the shape of water? That's the wrong question. The question, does it have shape? Okay, that's the way it works. And if it has shape, if all those atoms form some kind of shape, then those things are things. They're media. They're mediums, right? And they are objects for the purposes of physics. Do that now with energy. Do that now with field. Do that now with ether. What are you gonna put ether in a bottle and break it out there in space? Great. I want to see what it looks like. Well, what are you talking about? You talking about a bunch of particles? What is the ether? And that's where the problem comes in. They never define the ether. They never point to it. Either one. I mean, they can't define it and they can't point to it. And so we don't know what they're talking about, what's going through their little minds. We don't care what the real ether is, by the way. That's not important. What's important is his ether, the guy who's giving the presentation. We want to know his ether specifically because we need to understand his theory based on his ether. That's the way it works. Okay. Then we have these people who have borrowed irrational concepts from the mainstream establishment, and the worst part is that they've turned these concepts into physical objects. That's where the problem is. And here you have some examples: ionization, charge field, plasma, electricity, wave, time. You can go through several force. All these words have nothing to do with physics. None of them. Not one of those words has anything to do with physics. Not one of them is a physical object, but they treat them as if they were physical objects. They reify these words. And here you have another list, okay, but more or less the same one, essentially. It is irrational to use the following words as objects in physics. And here you have the words ether, plasma, electricity, charge, wave, space, field, and force. Obviously, it's not limited to these 8. None of those are things. Okay? So if you're treating them as things, if you're going to move them around, you're going to say, oh, the ether vibrates or electricity flows. No, electricity cannot flow because it's already flowing. And so they have the flow of flows. And they don't realize that they're committing a crime in physics. So none of these words are physical objects. Okay? And you can't use them as things, as media, as mediums, right? Can't use them as bodies. None of them qualify as things. And they don't understand that. It takes a long time for them to understand that. Some of them never do. And again, none of these have shape. That's the only criteria. Criteria is it's an object, a thing, a medium, if it has shape. Then it's an entity. All these words, by the way, are synonyms in physics. And there's no difference between them. You can use any one of them. Okay, and so what is irrational? Because we need to define also what irrational is, because we're saying that these people are using irrational concepts, meaning they're reifying these concepts and turning them into objects. And before I get there, they borrow also mathematical objects from the mainstream. They borrow the atom, the electron, the proton. They have the same models. And it's funny that these people criticize the establishment, and they're using the same objects, things that the establishment has fed to them in high school and college. And so, here's the notion of irrationality. There's several criteria, okay? And let's go through them real quick. Treating concepts as objects, that's the main one, because what they do is they take this concept, they treat it as a physical object, and they start moving the object. And you can't do that. It's irrational in physics to move concepts around. Then they have using inconsistent definitions or not defining words at all. And that's another crime that they commit. They don't have proper definitions. And then sometimes they put a definition, but they don't use it consistently throughout their dissertation. And sometimes they don't even care. They don't even have a definition. They don't realize that they needed that definition to make their case because people cannot follow their presentation. Theory, the explanation, right, is not consistent with the assumptions. I give the example in a crime. The prosecutor presents the knife as Exhibit 1, and then throughout his dissertation, his talk, he says that the person died of poisoning. Well, hold it. I mean, you presented a knife, now you're talking about poisoning. It's got to follow from the assumptions that you made. If you presented a knife, hopefully your theory is based on the knife, something to do with a knife. Okay. Then again, we have describing, especially mathematically, right, and claiming to have explained. A description is not an explanation. And some people have this notion or been taught this notion, and they just accepted it, that an explanation is just a series of descriptions. No, it ain't. Absolutely not. Explanation especially differ from descriptions in that you have a cause. You cannot get a cause from a description. And I'll give you an example, especially in today's world. You have all these invisible things like, again, here we have the, let me take this out. essentially, and the other one, mechanism cannot be imagined. But let's look at this. Here you have, again, my fork. Okay, you let go of it, and you can film it. You can take a snapshot if you want. You can describe what happened. You can measure. You can get all the equations you want. And can you tell me what caused it to happen? What caused that to happen? To come down. Why is it coming down? Why doesn't it go up to the ceiling? So we don't have a cause. We have a description. We have an observation. We can even have predictions. Say, hey, it's going to fall again. What we don't have is an explanation, a cause, a physical mechanism, a physical interpretation. That's where it fails. Okay, so what is these Aetherists come up with? And I'll just put one of them up here, okay? And he said the following. He said, electricity can flow through the vacuum, because I said electricity cannot flow through the vacuum, and especially under their version of electricity, because their electricity is the flow of something. The movement of something. Electricity is the movement already of something, whatever it is. I don't care what it is, but it's already the movement. Electricity is not standing still, like a snapshot. It's moving. And if it's moving, you can't talk about electricity flowing, because it's already flowing, it's already moving, it's already vibrating. So you're talking about the flow of flows. And so they don't understand that. They don't understand that language is important. They say, "Oh, Bill, you're very nitpicking, my theory." No, it's not that I'm nitpicking. It's that you're not making sense. Your language is wrong. Okay, so you got to fix your language. And again, they say that's semantics. It's word salad. What are you going to do? And then you can't go through the vacuum. By the way, why not? Because vacuum is not a medium. Okay, it's not a medium, and it's not a container, it's not a thing, and so you can't say this goes through. You can say it went through the ocean and went through the air, but you can't say through the vacuum. Vacuum, you cannot go through it because there's nothing to go through. Okay, so it's a wrong language. You cannot say through with the word vacuum, or with the word space, or with the word nothing. I went through nothing. Yeah, no kidding. And says no electron beads needed, no matter needed. So he's going to do without matter. He's going to do electricity without matter. And so I was waiting for a definition right there, right after those two statements. What does he do? He doesn't define the word electricity. He doesn't tell us what he's talking about. Like all ethers, he jumps directly into the theory. Like, okay, I fixed that problem, the electricity problem. Now let's work with it. And so he says, why does electricity flow in a straight line in a vacuum? No, wrong question. You haven't told us what electricity is. You cannot even ask that question yet. It's out of the it's out of the question. That question's out of the question. Electricity doesn't have to squeeze between atoms. He immediately jumps to conclusions, to the theory. You can't go to the theory. You haven't finished your hypothesis, with the assumptions. You haven't told us what electricity is, or you haven't pointed to electricity. You haven't defined it, so we don't know what you're talking about. And they don't understand that. They think that by doing so, you're just being, you're nitpicking their theory, or that you're doing word salad or whatever. For them, it's just noise in their ears. That's all it is. And he says electrons as ether. I don't know what he meant by that, because he says there are no electrons. Okay, but let's go past that one. Ether is incompressible. Yeah, because ether is not an object. That's why it's incompressible. But he says it's a continuous medium. And here we have two problems. The first one, it's not a medium. Okay, and it takes a long time for them to understand that. But it's not continuous. And he doesn't understand what he's saying. He doesn't really understand what he's saying. What do you mean? It's not it's continuous. Continuous means exactly the opposite of what he's meaning, and he doesn't understand that. He never realized. He's never gone through kindergarten physics, so he doesn't understand. Continuous means exactly the opposite of what he means. Continuous means made of parts. Let me repeat that. Aristotle came up with this nonsense. He said that if it's divisible, it's continuous. Got it? So don't use the word continuous ever, because to a mathematician, it means exactly the opposite of what he meant there. He thinks it's a the correct term is made of a single piece. So you don't use the word continues, you say it's made of a single piece. Then it's clear. Either it's made out of a single piece or it's made out of parts and you can chop it up. One of the two. But don't use the word continues because it means exactly the opposite of what he meant there. And he doesn't understand that, I guess. No such thing as an electron particle. Okay, so what is an electron? Why is he using the word, right? No positive or negative charges, and then he says only charge plus and charge negative, and discharge negative. So what is he talking about? We can't make sense of what he's saying because he says you can't use the word electron. There are no such thing as positive and negative charges, and then he says charge positive and discharge negative, whatever that means. He said cathode ray is a beam. You can't use the words ray or the word beam because those are not physical objects. Ray and beam are concepts, and you have to understand the difference between a concept and an object. And all these people don't realize that language is very, very important, and the reason mathematical physicists, theoretical physicists, the mainstream, the reason they cannot explain a single phenomenon because of language, because they have problems distinguishing between concepts and objects. They think a black hole is a physical object. It's not. It's a concept. Okay, it's an abstract concept. Space-time concept. Wormhole concept. All those are concepts. They treat them as physical objects, and that's where they get confused because they never define what an object is in the last 10,000 years. Okay, and here we have ether. It's continuous again. No, it's not continuous because continuous means something else. The opposite of what he meant. He says that the ether is not made of little particles. That's exactly what continuous means, that it's made out of particles. So he doesn't realize that. Okay, atoms are invisible, and we don't know what they look like. It's not what they look like. You have to tell me what your atom looks like. Okay, the one you're going to use for it to do your theory. So we don't care what the real Mother Nature, Father Universe atom looks like. We don't care about the real one. We care about your one. Okay, the one that you're going to use to do your theory. That's the one you want to illustrate that atom on the board. You can say, well, I don't know what an atom looks like, but let me tell you my theory. No way. Absolutely no way. We're not going to we're going to pull that microphone away from your mouth. And does that mean they don't exist? And again, we get the problem with the word exist because they think that they know what they meant by the word exist. Why do you think there are atheists, theists, and agnostics today? Well, because none of them define the word exist. That's why we have these three groups talking in circles. You need to define the word exist if you're going to talk about the existence of a chair or God or the angels, whatever. You want to know if God exists? Very simple. Define the word exist. And then you'll know if God exists or not. But if we don't know what the word exist means, then we're going to fight forever. Hey, I believe that God exists. Well, I don't believe that God exists. Well, I don't know if God exists or not. So we're going to be rolling around in circles. You want to know if God exists? Very simple. Define the word exist. That's how simple it is. That's how simple it was always. Okay, so what is the ether? Well, here we have... if you look it up like in the Google images, that's what you get. And so you say, well, what is all that stuff? Well, what they're showing, again, is particles. See, you see the arrows in the majority of them where the arrows go in one direction. And what they're saying, all these particles, gazillions of particles, they're flowing across the earth or across the sun, across the universe. That's what they always thought that it was. They say, all this stuff is flowing across the universe, and they imagined it as a bunch of particles just in the background. In fact, that's what ether means. It's air. The word ether means air. It's just the holy air of the gods of the Olympus. That's what it was. That's what Aristotle and his predecessors talked about when they talked about the ether. So that's what the ether is. If you have a different ether, you better make sure you point it out to us. Draw it. Make a picture of it so that we can see what you're talking about if you're going to use it as an object. Otherwise, you got to define the word. Very simple. And there you see definition. It says ether, a luminiferous ether was the hypothetical what? Substance. No, it's not a substance. Ether is not a thing, not an object, not a medium, through which electromagnetic waves travel. It was proposed by the Greek philosopher Aristotle, not true, it was proposed even before then, and used by several optical theories as a way to allow propagation of light, which was believed to be impossible in empty space. It was supposed that the ether filled the whole universe. And that's what all these people think, that there's this substance, whatever it is, made out of particles according to some, single piece according to others, and it fills the entire universe. And we have a problem with that because then, you've got, are you talking about a piece of the ether, or are you talking about the whole ether when you move it? And here you have an illustration of that, okay? Here's the ether that fills the entire universe. Okay, so it's made out of a single piece or maybe made out of parts, we don't care. Well, we really do care, because if it's made out of parts, you can talk about a region of the ether and start moving it, start vibrating it or whatever. But see, when you say that the ether vibrates, you're talking about the entire universe. You're saying electricity here locally, right, that comes into your cell phone, that's a vibration of the ether of the entire universe is vibrating. That's not what ether, you can't use the word ether anymore if the ether fills the entire universe. And that's the problem they have, because they're talking about a region of the ether, a small part. The palm is the region of a hand. Palm is not the same thing as the hand. So either you talk about the hand or you talk about the palm. And so you present the hand and then you say, something happened inside the hand. No, you're talking about now the palm of the hand. You can't confuse one with the other. Either you talk about the hand or you talk about the palm. Or China is a piece of the earth. It's a region of the earth. It's a region, right? It's a piece of the earth. Well, you either talk about China or you talk about the earth. You can't talk about both. You can't say, the earth moved. No, maybe China moved. Maybe there was an earthquake over there or whatever and moved the whole country, right? Then you talk about China, not about the earth. And this is the problem they commit here. They talk about the ether is filling the entire universe, made out of a single piece, according to this fellow, right? And then what does he do? He says, the vibration of the ether. Is the whole universe vibrating? Is that what electricity is? The vibration of the entire universe, Father Universe? Is he vibrating? And so this is the problem. You have to separate those two and treat them separately. You have to talk about a region, a small region, and then you got to give it a different name. Call it X. I don't care. But ether is the whole shebang. You can't say ether, the vibration of the ether is electricity and light and all this other stuff. Okay? And so when you say, what is electricity? A region of the ether that vibrates, not the whole universe vibrates. That's irrational. That's why language is important. These people don't pay attention to language. They say, I came here to do physics. I didn't come here to do English grammar. For them, it's just noise. They don't realize that it's important to define terms and to use them properly. Okay, so these people worship the Aetherists and electricians and so on. I talked about these fellows the other day. They worship these fellows one way or the other, and these are their heroes. And these heroes, especially Tesla there, these people had no clue about anything. They were not scientists. They were religious fanatics. That's all they were. They never really figured out how this universe works. And the reason, again, none of them defined the word object. You need to define the word object if you're going to do physics, because you can't do physics without objects. There's no action at a distance, no entanglement without a mediator, no such monster in physics. If this particle affects that one over there, there had better be some connection between them, physical connection. Otherwise, you are an irrational individual. You are invoking black magic. You are invoking the powers of God. That's what you're doing. Okay, and what's the problem with all these heroes that these people have? Well, the main problems here, this one, they all used the planetary model that Bohr and Rutherford invented. And this is a problem because, again, the little ball, the blue ball that's going around, it doesn't fall to it's negative, by the way, whatever negative means. It doesn't fall to the positive nucleus, right? And it doesn't fly away spontaneously. And so this is an irrational atom. Anyone using this atom it has an irrational theory. because whatever they found, if this is what their theory is founded upon, this assumption, this object, then they're going to have an irrational theory. And so again, this fellow says, well, we've never seen an atom. We don't know what an atom looks like. No, I don't care about the stupid real atom. I want your atom, the one you're going to use. Okay, that's the one I want illustrated. I need to see your atom. I need to see it on the board. I need to see what, and if you've got that atom, you had better be able to explain it before you move on to your theory. You can't say, well, this is my atom. Well, that's an irrational atom. So your theory is over already in the assumptions phase. You can't move to the explaining phase because you haven't finished with the assumptions. Okay, and here this is an article that came out this week, and I thought it was interesting, and it says again. So you can see there it says that what is an atom? The title is How Do Atoms Form, etc. But it says an atom consists of a heavy center called the nucleus, okay, and made of particles called protons and neutrons. An atom has lighter particles called electrons that you can think of as orbiting around the nucleus. And that is the atom that we have today from the establishment. That's the one everybody uses. And no, that's an irrational atom. And I like it because they put these hula hoops around it, and those represent motion, orbits, right? Because the little ball is orbiting, and so they have to put all these little lines there so that you know that, or that you can imagine that they're going around the center, the nucleus. This is the problem. The atom is just plain garbage. Okay, so what are the foundations of physics? That in order to do physics, you need to have these words. You can't do physics without these words. So we have these definitions, and you may again say, I don't like your definitions, Bill. They destroy my religion. No problem. Bring your definitions, be able to defend them. And believe me, I will really attack your definitions. I worked on my definitions for years. I've heard almost every argument that anybody came up with. So believe me, I'm an expert on definitions. I really am. Okay, so here it is. These are the definitions that I propose. First of all, we have the golden principle of physics. Physics requires an object. You can't do physics without objects. So we need to define the first word in physics you need to define is the word object. In fact, that's my biggest contribution to science, more than the rote model of light and gravity. No, it's the definition of the word object. That was a key milestone, a key cornerstone, right? Object, that which has shape. That's what an object is. An object's not that which you can touch, it's not that which you can see, and it's not that which is made of matter, occupies volume, has mass. None of those definitions are rational. That one there is a rational definition. I can defend it. Anyone who wants to attack it, no problem. Make my day. Space, that which doesn't have shape. So if something is that which has shape, nothing is that which doesn't. We're done. They're antonyms, okay? Space and object, vacuum and nothing. Nothing is the opposite of something. We're done. Then we can use them consistently. Distance, separation between two objects. Location, the set of distances. Okay, one object has distance with respect to all others in the universe, especially one atom with respect to all other atoms, right? And then we have the word exist, the one that nobody else either defined in the last 1,000 years. And again, object and exist are the main words to define in physics, because physics is the science of existence. What is exist? Physical presence. It requires an object, and what's the other criteria? That it has to have location. God wants to exist? No problem. First, he's got to be an object. Can't be a concept. You can't say, well, God is love. God is intelligence. No, that don't work. Okay? God has to be an object if he wants to exist, because the word exist belongs exclusively to physics. It doesn't belong to ontology, philosophy, metaphysics, any of those nonsensical categories they invented. No, it has to do with one thing and one thing only. Physics is the science of existence. It has exclusive dominion over the word exist. What is existence? Physical presence, meaning you have to have an object, and that object has to have location with respect to all other objects in the universe. Any atom in the universe has location with respect to all others. What does that mean for poor old God? Well, if he wants to exist, first he's got to be an object. Then he had better have location. meaning set of distances with respect to all other objects in the universe. There had better be a straight line of direction from God's chest to my chest. Otherwise, God does not have distance, and therefore he doesn't have location, and therefore he doesn't exist by definition, pursuant to the definitions. So definitions are extremely important. Motion, two or more locations of an object, and a concept. What is it? A word that invokes or embodies two objects. Okay. There is no object, no concept. There is no concept that has shape. So the quick way of determining if a word in the dictionary is an object or a concept: does it have shape? Can you imagine the shape of energy? Can you imagine the shape of of spirit, of force, of plasma? And some people say, I can imagine the shape of plasma. No, you cannot. You cannot, because plasma has never stopped moving. See, if plasma would stop, then maybe you can point to and say, okay, that's plasma. And you say, well, I can take a picture, a snapshot of plasma. Well, whatever you took a picture of is not plasma, because plasma is defined as ionized. Ionized meaning adjective, meaning verb, meaning motion. Ionized gas. So plasma never stands still, so you can't take a picture of plasma. Whatever you took a picture of is not plasma. And people don't understand those arguments, and, well, I'm sorry, you don't have the right stuff to do physics. Okay, let's move on to the subject matter today, the main course. Okay, and we have this thing called the Slit Experiment. What is that? Well, we have good old Richard Feynman. He tells us that thanks to this strange phenomenon called the Slit Experiment, thanks to that, what has happened is that quantum got invented. If it wouldn't have been for the Slit Experiment, we wouldn't have quantum today. They had to try to explain this experiment. They couldn't in 100 years. They tried to explain it with waves throughout the 19th century. And it worked to some degree, but then at some point they found that they could also explain it with particles by doing a little bit of magic. They still do magic with particles to try to explain it. And so what happened, they had the wave and the particle, and they merged both of them, and they said, look, it's got to be a quantum object. It's no longer a classical object. Classical object was a rational object that you can more or less wrap your brain around. You can say, okay, that's a ball. Okay, we all understand what a ball is, right? It looks something like that. That's a classical object. That's not what quantum is. A quantum object is something totally different. Quantum object means that it's got magical properties. It's Alice in Wonderland properties. You fall down the rabbit hole and see all these weird things. That's quantum mechanics. That's why they cannot explain a single thing in quantum mechanics. It's been proven. They can predict and blah, blah, blah. They cannot explain a single phenomenon. Therefore, quantum mechanics is garbage. It's garbage because you cannot explain. And science and physics are both about explaining. If you cannot explain, you're not doing physics. You're not doing science. So all they have is a mathematical description. That's what they call it's been proven. And we can predict. Yeah, with math you can predict. But you cannot explain. And that's the problem. We don't have explanations today. Okay, so he said, look, we choose to examine a phenomenon, the double slit experiment, which is impossible, absolutely impossible to explain in any classical way. Absolutely not, Dickie. You got it wrong. Yeah, we can explain it in classical way. In other words, with things that are imaginable. And which has in it the heart of quantum mechanics. In reality, it contains the only mystery. In other words, the slit experiment is the only mystery. Later on, they came up with entanglement, and that added to the mystery, but this is where it started. The mystery started with the slit experiment. That's how quantum got invented. And nobody can give you a deeper explanation of this phenomenon than I have given here. Well, I can. I'm sorry. I'm an exception. A description of it. Yeah, he's got a description, but not an explanation. That's what quantum mechanics is missing, and that's what people want. People want explanation. People want to know, how does gravity work? What causes gravity? And they say, well, let me show you what a field is, and field vibrates, and we have the black hole. They start going off into tangents. I want to know why this spoon falls to the floor. That's all I want to know. Just tell me. A very simple experiment, very simple thingy, right? and they cannot explain it. And then they never will, because later on they say that's philosophy anyways. We don't do philosophy in math, mathematical physics. What we do is numbers, we do equations. But then they also say, we're trying to find meaning to all this stuff, meaning explanation. They can't find them. Of course not. And so where did it start? Well, it started with this fellow. His name was Thomas Young. And he carried out an experiment in 1801 in which he found fringes when he had light impinging on a double slits. He cut these two slits, and he had light go through them, and he found out that instead of having two lines in the screen, he found all those fringes. And he said, what the hell? And so the problem was that with that he was able to destroy Newton, because he said, look, Newton was wrong. Light is not made of particles. It's made out of waves, right? Whatever waves are. And that supported essentially Huygens' version that light was, the medium of light were waves and not particles. But then the question is, what is waving? And that takes us back to particles, because what was the ether that was waving? A bunch of particles. So we never got away from particles. Since the days of the Greeks, we've always done particles. Even space-time is particles. And you say, well, is that true? Yeah, it's true, because first, you have the event, which is the important part of space-time. What is an event? A point in space-time. And then on the other side, you have also the fact that you've got what was it? Just escaped my mind. I had it for a second there. I'll get back to that one. Anyways, you have a particle world out there. That's what, whether you go with space-time or whether you go with quantum mechanics, you're going to have the same situation. Nothing is different between general relativity and quantum mechanics as far as that is concerned. It all relies on points. It all relies on particles, on discrete little points, because that's what the mathematician has to use. That's all he can put in an equation, a number that represents a point. And that's why the points, the particles, we've never gotten away from that. Okay, so here we have a fellow who tried to explain the slit experiment. His name was Augustin Fresnel. And he put this picket fence analogy, which was that when you run light through a polarizer, and he just imagined that as having vertical direction, okay, and what that does is cut out any horizontal component of light, and what continues is only the vertical portion of light. And if you put another polarizer later on, which is at 90 degrees to that, it eliminates the horizontal component as well. And so with this, he was saying, look, he confirmed first that light was a wave, that you cannot explain this phenomenon with particles. And second, he says, hey, not only a wave, we've got something different than what Huygens proposed, which he was thinking about maybe water waves. That's what he was analyzing, Huygens. And this fellow says, no, it's transverse waves. It's waves that go forward, but they're moving up and down perpendicular to the direction of motion. That's why they're called transverse waves. And it had two components. And later on, we have our good friend James Maxwell, who came up with this notion that that we had two components to it, the electric field and the magnetic field. And these are the fellows who dealt with that throughout the 19th and 20th century primarily, even to this day. And you can see what's wrong with it. They're talking about fields, which are valued at each point in space. That's how the word is defined. And so those curvy lines that are containing the arrows, those curvy lines, those are the so-called fields, right? And the vectors, what are they? Magnitude and direction. What's magnitude? Numbers again. So we have values and numbers. Values and magnitudes. That's what you're seeing. So this is an attempt to pictorially represent a mathematical concept. That's what it is. And so this doesn't belong in physics at all. And it's even funnier when they put this thing in motion and have the wave, the electromagnetic wave, move in this case like to the right, one way, and they always move one way. And so this is the notion we have to this day from the mathematical establishment. Okay, so here we have the explanation of the slit experiment according to these waves, right? They say that the source of light just sends waves through the two slits, and these waves later on interfere with each other, sometimes constructively, sometimes destructively, and those are the ones that cause the fringes. Okay, there you have more or less an idea of what they were proposing throughout the 19th century, that this is the explanation for the slit experiment. But then we had a fellow at the turn of the century, and his name was Max Planck. And what he did was he came up with this notion that, light or energy comes in discrete packages. And that's where the quantum came into being. Okay, so he came up with these notions that light comes in discrete packets, and eventually they were called photons. So today we have the photon, which are these discrete packets, but what's the issue? Oh, that was the thing I wanted to say before. You have the field. And what's the problem with a field? The field is the local vibration. In other words, a particle is a local vibration of the field. So even though you have this field which extends throughout the universe, locally you have the vibration of the field, and that is what a particle is. So again, quantum mechanics and general relativity are both particle theories. They're both particles. They've always had particles. They never got away from the particle hypothesis. That's what the problem is. And this is the issue. Unless you destroy the assumptions of mathematical physics, you destroy the discrete particle, meaning the field, meaning the energy. When you destroy all that, then you can start making some progress. We have to erase the board completely and start all over again. They never hit it on the nose. Okay, so here we have the slit version, the particle version of the slit, right? And this is more or less the notion they have today from the particle. The problem with this is that they have one particle. In order for it to interfere with itself, one particle has to go through both slits at the same time. And that's what they came up with for the particle version. So we have either the wave version, which is, we don't know what a wave is. It's not a physical object, so it's a bunch of numbers, but we have these waves. They go through two slits and they interfere. So we have these concepts that are interfering with each other. What is the particle version? The particle version is the particles hit the slits, the sills, the window sills, whatever, and but it's one particle that has to fork out somehow, divide itself. Half a ball goes that way, half goes this way, and then they interfere with each other at the screen. So those are two versions. Take which one you want. Just in case, we had a couple of people. Merli was one of them, an Italian fellow, and then another fellow, a Japanese fellow. His name was Tanamura. And Tanamura ran experiments with single electrons. Okay, and this is more or less what happened here. Oh, I see. Hold it. There it is. This is Tanamura's version of handling one electron at a time. That's how he concluded that electrons are little particles. This is what he has to say. There's no sound on this one, so you'll just have to read. Okay, here it goes. Well, the only important statement that Tanamura made was that last one. Yeah, it's irrational what they concluded. And no, electrons are not particles, and we cannot prove that, like he said he proved it through experiments. Okay? And we'll find out why here. But the first problem with Tanimura's version that he handled one electron at a time is he used Bohr's version of the atom. He had this notion, that the electron bead is something that orbits the atom. And so Tanimura would not be able to defend this atom. Therefore, his conclusion that electrons are little beads, little particles that hit the screen one at a time is totally irrational. It's irrational because he cannot justify his atom, the one he used to make that statement. So that's where his problem comes. Anyone talking about handling one electron at a time has to first show me his atom. Show me your atom. And I'll tear his atom to pieces, and therefore he cannot even get to this theory to explain how that works. That's why nobody can explain anything today in mathematical physics, especially in quantum mechanics, because they don't have the right atom. We have a wrong atom. That's the problem. Okay, so because they have this irrational atom, they conclude that we have these electricity is just a flow of all these beads. That's their notion. So they say, okay, we have all these beads, they're moving around, and that's why we have the pattern on the screen that has all these bullet holes in it. Okay, so this is how they came up with all this stuff. And so what we do, we have a different atom that we present. It's totally different than the one that Tanimura used or that Niels Bohr and Rutherford used. And it looks like that. You can see the quantum atom versus our atom. A little different, I think, right? We have a different atom. And ours is a physical atom. Theirs is a mathematical one. You see all the ropes from every atom in the universe. And again, these ropes are extremely thin. Unimaginably thin. If you were Atom Man, maybe you could take a picture of them up close and then bring it up to us. But you're talking about two twined threads, DNA-like, and we think that's where DNA got its form, its structure, its architecture. It got it from the rope, because the rope is what underlies light, torsions of the rope. And then the atom is just made out of the same threads that make up the rope. One thread goes through the center and becomes the proton star, and that's encapsulated by the electron shell or electron membrane. So you can see we have a little different atom than the one that quantum has, and no, electron is not a bead. When they talk about a bead, like when they look at the quantum numbers, they're talking about a point that they measured on the surface of the atom. So our model is consistent with, by the way, with Schrodinger's equation and with quantum numbers. It's that we have a different interpretation for it. We're saying that what all these people have been doing for all these years is really confusing a point on the surface versus being it a bead. It's not a bead. It's not a little dot there that moves around. They just identified a point on the surface of that membrane, balloon. Okay, that's what it is. So we have no problem with the equations. Ours is consistent with the equations. In fact, it's more consistent also with chemistry that uses, actual balloons, merging of balloons, and whereas the Bohr atom has to do it with orbitals. And what is an orbital? Is that a physical entity? No, it's a bunch of orbits. It's the region where you can find the electron bead. And so they're merging regions. Region is a concept. You don't merge regions, not in physics. Okay, so what is our model of electricity? Well, again, we have all these atoms. They're screwed into each other. They're merged, right? Like figure eights, more or less. And they rotate. And when they rotate, they create what is known as the magnetic field, which is made of all the threads, again, that are just swinging around at great speeds, and that is the magnetic field. So the magnetic field is really made of threads out of physical objects. It's not an abstract thing because you can't see it or touch it. And but that's what they concluded, that they can't see or touch, so it must be nothing. All these lines, that they see with little iron filings. Okay, so what's the problem with Tanimura's bullets? How do we represent that? Totally different. Nothing to do with bullets. It's like a drill. You got to think of it as a drill. Okay, here it is. This is the rope version of how those little dots are made on the screen with the during the slit experiment. So here it is. You'll see it for the first time. That's how we do it in science. And when we make many of these, then you'll see it on the board. That's what you'll see. So electricity is a drill bit, okay? And what it does is you have to have a long line of molecules, really, not really atoms. We do it with atoms just for ease of explanation, but really it's molecules which are merged with each other, and they drill in situ. So there's a long line of molecules pointed at the screen. And when you have that, then yes, you can make these holes that they're talking about. Okay, you can make them with molecules that are actually drilling into the wall. Okay, so this notion that they handled one electron at a time because that's what they think electricity is, we're replacing that with a drill bit. We're saying electricity is a long line of merged cells that drills in situ. You have to have atoms in order to do electricity. These people do it without atoms. They just have the electron beads flowing. They say, oh, we handled one electron bead at a time. No way, because that requires the Bohr atom, which is an irrational atom. You can't justify your atom, so your theory dies at the supposition, at the assumption stage. Okay, so we come to these two fellows. One is Matt O'Dowd, and the other one is Sabine Hossenfelder. And they're going to explain to you all the knowledge we have, meaning mathematical physics, the establishment, right? All the knowledge they have about the slit experiment. So let's listen to them, and it's going to be directly from the horse's mouth. Here's Matt O'Dowd first, beginning by telling us how rational, or better yet, how irrational, right, quantum mechanics is. He doesn't understand squat, but he accepts it, that he just learned it by rote and just regurgitates it by rote. So here it is. Listen to him.
I remember hearing about the double slit experiment. I thought, oh, magic is real. Of course, quantum mechanics is not magic, but it was this peering beyond this, the intuitive and the stuff that for all my life felt just this regimented thing that physics was. I think there is this mystical quality to quantum mechanics, which is why maybe it felt like that to me. There's this totally unanswered questions at the very bottom of quantum mechanics that defy intuition.
Yeah, quantum mechanics defies intuition, meaning it's irrational. That's what he meant. And people don't want to use those strong words. They say, oh, are we going to say that it's irrational? Yeah, quantum mechanics is totally irrational. You cannot make sense of anything in quantum mechanics. But if in doubt, let's listen to, here we have Sabine Hossenfelder. She'll say more or less the same thing. So I want to make sure that at least two mathematical physicists say, so that people don't say that I'm the guy who's saying it. No, it's they themselves. Here it is. Listen to her.
I learned quantum mechanics like most students those days, I guess, from a professor who was like, don't ask what it means, this is the maths, don't ask about interpretations, stop thinking. It was literally this shut up and calculate attitude.
Okay, so they start out their presentation by saying, oh, by the way, quantum mechanics is irrational. Don't try to make sense of it. Let's continue. No, we can't continue. We got a problem there. If it's irrational, what are you going to teach? Math? Just descriptions? And so they talk about the main interpretation of the slit experiment, and it's the Copenhagen interpretation, and it's quite irrational. But again, let them speak for themselves. I'm not going to intervene here. I'm going to let them make fools of themselves or of their religion, and they believe in this religion. They say it's been proven, but this is what they believe in. While they're telling you that they don't understand it either, that the Copenhagen interpretation is no interpretation at all. Here's Matt.
The standard interpretation is the Copenhagen interpretation, which really just says that things exist as wave functions until a measurement is made, and then the wave function collapses. I call the Copenhagen interpretation the non-interpretation interpretation of quantum mechanics, or the shut up and calculate interpretation, because it's not really an interpretation. It's not telling us what's happening when a measurement's made. It's just saying the wave function collapse just works. That's where we've been stuck for 100 years.
So from one generation to the other, they've been teaching the same thing. They say, look, shut up and calculate. Niels Bohr said that. And they teach one generation to the other. And the people come in the first day, a freshman, or even at the sophomore and beyond level. And they go in there and they listen. They say, okay, if that's what they've proven, who am I to question that? And so nobody questions all this irrationality. They just accept it. They say, well, if they ran the experiments and this is what they came up with, well, we have to accept it because they know more than we do. And that's where we're at today. All these people have been brainwashed with the same catechism, and they came up with the same irrational notions. They keep passing it on from generation to generation. Here's good old Hossenfelder saying the same thing, essentially. What does she have to say about the Copenhagen interpretation? Well, here it is.
The Copenhagen interpretation was basically Bohr's idea. Let's just not ask what's going on. This isn't real. We're not supposed to ask that question. Shut up and calculate, basically. So I'm not sure it's good to talk about causality, because we know that causality gets really screwed up in quantum mechanics.
Okay, so what do we have? We have irrationality. That's all we have. And they say, look, it's not an interpretation, but shut up and calculate. That's what they teach them. And so they learn by rote. They just memorize whatever they were told. Nobody's making sense of the Slit Experiment. They haven't been able to make sense in 100 years. Okay, and just in case, there's another one, which is the many worlds. And briefly, here we have Sabine tell us a little bit about that one. And again, it's all irrationality. We split up in a million universes, gazillions of universes, and in one universe you win the lottery, and the other one you're dead. And this is more or less what the famous many worlds version is. Here it is.
I think the best known interpretation after Copenhagen is probably the many worlds interpretation, which says, loosely speaking, that whenever you make a measurement, you create a new universe. So all possible outcomes actually do happen. So the particle goes to each point on the screen, but for each possible outcome, you get a separate universe.
You come out of a different universe. Does that make any sense to you? And again, it's all irrational. We don't have an interpretation for an experiment that we've known about for over 200 years, and that's incredible. Now, what I did? First of all, you don't need the slit. That's the first thing I want to show you. Okay, here I have a needle. I left the thread so that you can see the needle, just in case you couldn't see it. Okay, but we have a needle stuck to a cork, right? And we have a laser. Okay, I'm gonna put a laser. This is not a laser. It's got a laser, but I'm not pressing the laser button. The point here is you're gonna shine a laser at the needle, and far away, a few meters away, you will see the fringes. You don't need the two slits. They've always done it the hard way. And why is this important? Well, it's important because if I can shine a laser on a needle and produce the fringes, that means I don't need to send them through two little slits. But it means also, if it's particles, the particles have nothing to bounce against on the outside of the needle. See, with the two slits, people think that light is bouncing off the sills, the window sills, right? And that's not the case. The case is because if you remove the window, so you just leave the center part, and you still get the fringes, then obviously, it's not little particles that are bouncing off something and coming in towards each other. Same for the wave. What is the wave bouncing against? The wave is sent, allegedly sent, from the source, from the laser, hits the edges of the slits, right? And then, they interfere constructively and destructively on the screen. But if you remove the outside of the slits and just leave the piece in the center, now what happens? You still have the fringes, but now you have nothing to bounce against. And that's where the problem is. That's why light cannot be either a particle or a wave. Cannot be mediated particles or waves. Waves being a concept anyways. So I did the experiment at home. This one I just showed you with the little cork, needle in the cork. And there you see the needle in the cork. And at the far end you see a little light on the wall. And that's what it looks like. You can see the fringes there. Very crude experiment, nothing fancy, but you don't need the slits to do this, but you can see the fringes anyways. That's my point. So you can do this at home in the privacy of your home. You don't have to take my word for it. You can produce the fringes on the wall, okay? So what's the issue? The issue is how do we explain the slit experiment, which good old Dick Feynman says, it's impossible to explain in a classical way. Let's explain it in a classical way and forget about the nonsense of quantum mechanics. So here it is. Okay, here's the explanation for the slit experiment. Okay, we have the light is, when the laser is turned off completely, you already have connections between every atom in that room. You have a connection between the atoms that are in the light source to the atoms that make up the needle to the atoms that make up the wall. So all you're going to do is turn them on. You're going to increase the frequency, right, by turning the laser pointer on or whatever you use as a source, and suddenly all those ropes are going to torque at a faster speed. Okay, it's really the same speed. What's going to change is the frequency versus the wavelength. The wavelength is going to become shorter, and the frequency is going to be greater. Meaning you're going to have more goosebumps, for any given rope. That's what it is. That's why light comes, into our eyes. We can see, right? You can see this light suddenly turn on. And what happens when you do that, you have the same notion that we have from wave theory, where you have one wave which is offset with respect to the other. And you can do this with your hands. Let's see if I remove this, I can show you. Okay. Imagine putting your hands there. Well, all you need to do is move it to the side. Let's do it in this direction. You move it there, and you see what happens. You're off by half a wavelength. Right? And that's the issue. The issue is that when you have the light at a given angle, you're going to have regions where you have this dark fringe. Why? Because the waves are out of phase, and so they're impinging on the screen destructively, whereas at a later point they're constructive, destructive, constructive, destructive. That's what it is. Very simple stuff. And here you have a comparison between the waves that quantum mechanics offers and the rope model. Okay, the rope model's on the right there. And you can see that our mechanism is totally different in the sense that we're using physical objects. They're using this concept called a wave. Whatever that is, wave of what? We don't know. We never have figured that one out. And so they keep insisting on the wave. Particles cannot explain it. You need to have particle at two places at once. And that's rational in the religion of math, but it's not rational in science. And so we can't use the particle at two places at once. We can't use the wave. That leaves right now the only valid theory that light is made of ropes, torsion of ropes. That's what light is. So very easy, really physical system. Here you have a rope, okay? And what we're saying is that, if you want light, you need to, this is dark light, long wavelength, few links, meaning small frequency, big wavelength. And if you tighten this, right, you get more links, and each link is shorter. And that's the little c there, which is c is equal to c being the velocity of light, a constant, is the inverse relation between frequency and wavelength. That's why light is a constant. C equals frequency times wavelength is the equation of a rope. And they never figured that out. They always messed around with the wave, and they never could explain why they cannot increase both the frequency and the wavelength and travel faster than light. Tachyons or whatever. They never figured it out. Why? Because they never figured out that what they were staring at is not a wave, a transverse wave, it's a rope. With a rope, now we can explain the slit experiment, we can explain gravity, and we can explain the atom as well. The atom is a totally different monster than what quantum mechanics has proposed. With that, I'll see you